Logical bound for threefold. So X for us would be a smooth projective threefold. Defined over the complex number. And we said that in the course of Capallo and the course of the bar that a lot of the geometry of X is encoded by the behavior of Kx, the canonical bundle. Then another important object is the section ring of the canonical bundle. So we call it Rx Kx, so the graded ring of section. So let me just restart recalling you what's the general conjecture of the MMP. So we say that we start from X as smooth variety, and if the Cotary dimension of X is non-negative, then it's possible to associate to X a variety Y birational to X such that Ky is an F, and we call Y a minimal model. Otherwise, if I don't have any sections, so if the Cotary dimension is equal to minus infinity, then X is birational to Z that admits a fibration with fiber or Fano, and we call it a Mori fiber space. So for the talk of today, I'm just interested in the first outcome. In particular, I want to consider the case of general type, so maximum Cotary dimension. So in this case, the canonical divisor is big, and X is of general type. So in this case, we are in dimension 3, so the MMP works. We have a smooth variety of dimension 3 of general type. So we know that the minimal model exists. So what I would like to talk about today is the possibility to find a bound for the number of minimal model of X. Now let me just make a vague remark here. So this kind of problem is also related to the possibility of finding a bound for the degree of the generators of the canonical ring. Of the canonical ring, and also the weight of the relations among the generators. I want to bound the things, and so today I'm just going to focus on the first problem, bound the number of minimal model of X. And both bounds are going to be depending on the topology of the underlying complex variety. So in particular, depending on the Picard number. So the Picard number, it was said before, is the dimension of the Néron-Severi, so the divisor modulo numerical equivalence. Why I say that it is a topological invariant? Because it's possible to bound it by the second Betti number. So this is just the dimension of the H2 XZ. So it doesn't see the complex structure. So let me start with an introduction and motivation. So I just want to give you an idea where these two problems came from and why they are somehow related. So we're going to start with like a smooth projective variety. So for simplicity, we assume that X is smooth, but the technical property that I really need is that S is Q factorial. So every Weil divisor is a Q Cartesian factorial. And then we are going to assume that there exists divisor D1 dr, Q divisor in X, such that when I look at the multigraded ring, so the generalization, if you want, of the canonical ring, so D1 dr, I'll take the space of multisections, so N1, NR, then to dr, and 1D1. So this is called the multigraded ring of section, and I'm assuming there exists some divisor such that this ring is finally generated. So if you just have one divisor and it's a canonical divisor, it's exactly the canonical ring. So I made this assumption, and let me remark that there are two important classes of variety for which this assumption is satisfied. So the first class is the varieties for which the MMP works successfully. So for example, there is a famous result. So if I consider some divisor delta I such that the pair x delta I is KLT, we saw the definition yesterday, so a special class of singularity, and such that kx plus delta I is big, so we have some sort of positivity, then the famous result of Birkar, Cascini, Aiken, McKernan tell you that the ring associated to this divisor, kx plus delta 1, kx plus delta r, is finally generated. This was an extremely important result, and from this result you have the existence of minimal models for log general types. Of log general type. So if we work with a variety from which the MMP works, then this assumption is satisfied. Then what is the second class of variety from which we can assume that we have the finite generation of this ring? So we assume if we are on a variety X such that the Picard coincide with the Néron-Severi, and we consider as D1, dr generators of the Picard, then this ring is exactly the Cox ring of X, so Cox ring. And if the Cox ring is finally generated, I consider as a definition a variety for which the Cox ring is finally generated is called a Mori dream space. So take it as a definition. So if we are on a Mori dream space, then the assumption is satisfied for every divisors. So as you see, it has a very special name, and we'll see in a while why it's called Mori dream space. So if we are in this context, so if you assume that the ring is finally generated, then I can consider the span of all the divisors. So D1 for one that goes from 1 to R. So inside the class of R divisor in X. And then the final generation of X, so the fact that the R, is finally generated, give us a decomposition of the space of divisors. So the final generation tells us that we can decompose the space of divisors into a certain number of rational columns, and that finitely many. So from the final generation, we obtain a decomposition in finitely many rational polyhedral cones. And what is special about these cones? So for each divisor inside one chamber,
S is sum of R plus.
Yeah, okay. But it's, yes. So we have a decomposition in a finitely many rational cone, and for each divisor inside a chamber, it's possible to associate a birational morphism from X into a certain Xj, such that the push forward to divisor D is going to be an F divisor on Xj. So if you want, this is kind of, we call it this an F model, and this is a sort of DMMP. So the classical MMP tells you that you can do such a thing when D is the canonical divisor, or a log version, so the canonical divisor plus an effective divisor. But here, you tell, when you are in a Moore-Dream space, for example, you can do the same things for every divisor. So this is why it's more a dream space, because you can run the MMP for every divisors. So this kind of technique is called Shokурov geography. This is the Shokurov geography of model. And so it was introduced by Shokурov, and it has extremely important application. We used to prove the MMP with scaling, the Sarkisov program, but more important from what I'm going to do, later in the talk, using this kind of technique, you can prove the following theorem. It's kind of, it's a theorem, or theorem conjecture, because it basically assumes a lot of conjecture. So if you assume the full MMP, so the MMP abundance, and so basically assuming the full MMP, you can use the kind of technique of Shokurov log geography, plus another conjecture that I'm going to, first going to state it, the relative version of Kawamata-Morrison cone conjecture. I'm just going to say later what it is and why it's important. Then the number of minimal models of a smooth projective variety is finite up to isomorphism. So assuming the Shokurov log geography and this other conjecture, you can prove that the number of minimal models is finite up to isomorphism. So in the case of general type,
so that is for any dimension?
Yeah, for any dimension. But so if X is of general type, then it was proved by, again, Birkar, Caccini, Akon, McKernan. And for the general type case, you don't need to consider the Kawamata-Morrison conjecture. So they proved that the number of minimal models is always finite. You don't have to consider isomorphism. And what they did was exactly proving this kind of statement, so the finiteness of minimal model using Shokurov log geography. If you are in a variety of, so this is the case, and let me get, so a general type was proved, and you don't need to consider the isomorphism case. So this is a case that is going to be important for us. But let me just in general, let me just say some words about the second part. So if you work with X that is of intermediate codary dimension, then the full MMP, so in particular abundance conjecture, tell you that you can associate that X admits a minimal model that admits morphism was fiber R Calabi-Yau. So this is a bit vague, but just consider that in the case of intermediate codary dimension, at a certain point, a fibration was fibrous Calabi-Yau arise. And the Kawamata-Morrison conjecture, it regards Calabi-Yau varieties. So Kawamata-Morrison conjectures tell you that if you have X a Calabi-Yau variety, then you consider the action of the automorphism group. So then the action of the automorphism group of X on the F cone admits a fundamental domain that is rationally polyhedral. So if you want, the Kalamata-Morrison conjecture is kind of the step forward to the cone theorem. The cone theorem tells you that the negative part of the cone is rationally polyhedral. So if you have a Fano variety, then of course all the cone is inside the negative part and the cone is rationally polyhedral. As soon as you work with Calabi-Yau variety, this is no longer true. But the Kalamata-Morrison conjecture tells you that up to the action of the automorphism group, then you obtain a fundamental domain that is rationally polyhedral. So these are the two ingredients that you want to prove this theorem.
And can you still contract the stringal rays of those?
It's more complicated.
By Calabi-Yau, you just mean that the canonical is trivial?
Canonical trivial, yeah, I
Can
guess.
include also an abelian variety?
I'm not sure. Not sure about it. I don't know if they have assumption on the simply connected or something. I'm not sure.
So in the first case, you mean that there are finitely many Mori chambers of the effective cone?
Yeah. Here it's a decomposition in finitely many rational polyhedral chambers. So if we work with a threefold of general type, then the ABC term tells you that the number of minimal model is finite. And so it makes sense to ask for a bound. How many are this number? So the first result of bounding this number in terms of the Picard number is a result of 2003 by Cascini and Lazic in the case of log general type. So they consider a pair of log general type with a strictly non-zero boundary, and then they found a bound depending on the Picard number of X and on the Picard number of the component of delta. And then they conjecture that also in the case of a smooth threefold of general type, the number of minimal model is bounded by a constant depending only on the Picard number. And the number of minimal models is bounded by a constant m depending only on the Picard. So obtain some results towards the conjecture. The first one is the technical theorem, in the sense that we are able to prove the conjecture under a technical hypothesis. And the technical hypothesis is the following. So we assume that we can run the MMP doing first all the divisorial contraction, and then all the flips. Then under this technical assumption, the conjecture holds, and the bound is something like 3 rho x minus 2 rho x minus 2 factorial squared. So this is a technical assumption in the sense that in general it's not going to be satisfied. By using this technical theorem, you obtain some corollaries. So the first one,
Factorial? Is that a factorial?
yeah. And as a corollary, we are able to find a bound in case of low Picard rank. So if X is a smooth threefold of general type such that the Picard is 3 or 4, then the number of minimal model is at most 3 or 72 in the case of Picard rank 4. So for the corollaries, we don't have any assumption. It works in general. If you take a smooth threefold of Picard rank 3, then it has at most 3 minimal model, or 72 in the case of Picard rank equal to 4.
Yeah, but do you have examples where you get that bound?
No, not yet, but just because it was very recently I found a way to to attain a bound that was sharp, or at least much sharper. Before, the number were much greater, and so, I mean, now that, that we have such a small number, it makes sense to ask for an example. But I didn't have time to look for it yet. So let's just, let me mention then, I mean, 3 and 4 are the first non-trivial case. I'm going to say later why. Picard rank 1 and 2 are trivial. So just a vague idea of the proof. So we start from X, smooth, threefold of general type, and then we are going to look at the graph below X. So basically we are allowed to do divisorial contraction and flips, and want to count the endpoints below X. So the strategy is first bound the number of steps, of the MMP. So in at most how many steps I reach an endpoint, and then bound the possible number of operations from going to one step to the other. 4 to xi from xi to xi plus 1. So in how many ways I can go from one step to the other using a divisorial contraction, and in how many ways I can go from one step to the other using a flip. And let me just mention then the difficult case is bound the number of flips. So in how many ways I can go from one step to the MMP to the other using a flip? That's a difficult question. So I'm just gonna, the last 5 minutes, I'm gonna give you an idea of how to prove the bound for the number of steps. So proposition, the number of steps of the MMP is at most 2 rho x minus 2. So first, let me make a remark. If you consider x minimal, we can assume that the Picard rank of the minimal variety is greater or equal than 2. Why? Because if it has rho x equal to 1, then it means that the canonical bundle is either ample, anti-ample, or trivial, but we are on something of general type. So it means that kx is ample. And in this special case, we already know that the minimal model is unique, so it's not an interesting case for us. So I'm just going to stop when I reach Picard equal to 2, Picard rank of the minimal variety equal to 2. So how do we bound the number of steps? So the number of steps is going to be the number of divisorial contraction and the number of flips. So the number of steps equal the number of divisorial contraction and the number of flips. So bounding the number of divisorial contraction is easy. All the time, so I go from x to x min, and all the time that I do a divisorial contraction, the Picard rank drops by 1 because I'm contracting one divisor. So of course, this number is exactly going to be rho x minus rho x min, and I said that this is greater than 2, so this is at most rho x minus 2. So if we want to bound the number of flips, the Picard rank is not going to help us because the Picard number is stable under a flip. So we need to introduce a new parameter. So for the flips, I need the so-called dx Shokuro difficulties. So as the name said, it's something complicated. And I'm not going to tell you what it is. I'm just going to tell you what it does, and I'll leave Paolo the task to find the difficulty later. So the difficulty is something that kind of, let's just say, measure the singularity of x. And why is it useful if we want to bound the number of flips? So the flips strictly increase the singularity of my variety. So and a flipping curve has to pass through a singular point. So let's do the first step. So if at the beginning I'm starting with x smooth, so no singularity, and the difficulty is equal to 0. And in this case, I have no flips. Because the flips strictly increase the singularity, smooth it cannot be better than smooth, so I don't have any flips. So the first operation of the MMP is always going to be a divisorial contraction. And then we are going to see how the difficulty changes when I have a divisorial contraction and a flip. So if I'm going from xi to xi plus 1 with a divisorial contraction, we saw that starting from dimension 3, if I contract a divisor, I can produce singularities. So the difficulty might increase. But it's possible to prove that it might increase, but it increases at most by 1. Then if I do a flip, then the singularity are strictly increasing, so the difficulty decreases. But it decreases always at least by 1. So what's happening? I start from something that is smooth, so difficulty equal to 0. I have a divisorial contraction, so I might have a flip. I might have some singularities. But then I do a flip, and the flip strictly increases. I go back to difficulty 0. So the moral is that in order to have a flip, I first need to have had a divisorial contraction. So again, here, if I want to bound the number of flips, is bounded by the total number of divisorial contraction. So this was rho x minus 2, and so the total bound is 2 rho x minus 2. So let me just give you an idea of what's happening for Picard rank 3. So I take x, Picard rank equal to 3, and the difficulty is 0 because I start from something that is smooth. So how many? I'm going to have at most 2 rho x minus 2, so just 2 possible steps. So the first one is always going to be a divisorial contraction. So I do a divisorial contraction, and I reach x prime, rho x equals to 2, and I might have created some singularity, so the difficulty might be bigger than 0, but in particular smaller than 1. And then, so the only thing that I'm allowed to do, since the endpoint is always Picard rank 2, is a flip. So at most I can do a flip. And then again I have rho x equal to 2, and difficulty equal to 0. And I stop. And then here it's possible to prove that in this case, this divisorial contraction can be realized in at most 3 ways. 1 divisorial contraction to a point, and 2 divisorial contraction to a curve. And then it's possible to prove that if the last operation of the MMP is a flip, then it's unique. So here I have at most 3 endpoints. So in this case, the case of Picard rank 3, it's easy because it is exactly satisfy the hypothesis of the technical assumption. I just have 2 operations, 1 divisorial contraction and a flip. The case of Picard rank equal to 4 is much more complicated because it does not satisfy the assumption on the theorem, but still is kind of, the graph is small enough that you can work it explicitly and look every operation and understand the value of every arrows in the graph. But it's more complicated. And I'll stop here.